Okay, so today is going to be probably a really short lecture because we have only this one topic, and because I don't want to start another topic that is kind of disconnected from this one in this lecture. So here I made a review of the most important points for this topic, and for actually operating doing computations, the operator product expansion that we discussed in the previous lecture. Okay, and what I have to keep in mind is that CFT, we've learned that CFT is composed of primary and descendant fields and states. Recall the primaries, fields and states are annihilated by the special conformal generator because it acts like a lowering operator for the scaling dimension, the field or the state. And the descent is then defined as just a bunch of momentum operators, generators acting on these primaries. And we see that for a given primary, we have an infinite number of descendants, and all of these descendants plus this primary constitute what we call a conformal family. Okay? And then if I pick another primary, I have another conformal family, and so on. Okay? So that's how the given space of the theory is separated. Okay? Also, by the operator state correspondence, we learned how to map primary fields on the primary operators. Remember that on CFT we can speak of fields and operators interchangeably. Okay? They mean the same thing. So if I change from the another, it may sound a bit awkward at first, because it's not why we say standard point of view theory, but you must get used to it. Okay? So by the operator state correspondence, we learn how to map fields and operators at the origin to all of the Hilbert space states of the theory. Okay? There was an isomorphism and we called the operator state correspondence. So what it means that from this knowledge, in terms of say the operators, we can get the states and vice versa. And this means that a CFT is characterized by the spectrum of its primary operators, or states. Okay, and by spectrum, this means the scaling dimensions and their speed. Okay, and just a reminder that because from the conformal algebra, the scaling operator and the rotation operator can use, so we can measure both properties simultaneously. Okay, and no others. And but we've been working so far only with the scalar fields and scalar states. Okay, and dropping this thing for now. Maybe in the next lecture I'll come back to the spin structure to spinning fields. Okay, when we discuss the moment test. But for now we just focus on scalar fields and states. And here just the correlator functions, the correlation functions that we computed by the Lightning formalism. Again, the 2-point function is completely fixed by the conformal symmetry. If the two fields here have the same scaling dimension, then the correlator became like a power law dictated by the scaling dimensions, delta. And if the scaling dimensions are different, the correlator vanishes. Okay? For the 3-point function, we found we managed to completely fix the functional form. This again a power law behavior. But we have an undetermined constant here that depends on the fields times here. That's what this 1, 2, 3 means. Maybe I should. If you're dealing with a more complex theory with scalar fields, scalar fields, and so on, it's better to just write the fields itself here. Okay? But since we're only dealing with scalar fields, identical scalar fields, and so on, I'll just write the numbers. Okay? But keep that in mind. And we have just this undetermined constant that we called the structure constant, which again has nothing to do with structure constant from the algebra. Okay? It's just the same name. And finally, for the 4-point function, we learned that we cannot even fix the functional form completely. We can factor some kind of ordinal behavior here, but we still left off with an arbitrary function of the conformal invariance, U and V. And this arbitrary function is known as conformal block. Okay, and if you keep playing the game for 5-point functions, for example, you would be able to factor out some ordinal behavior in another function, but now you have like for 5.6 conformal invariance, which you can construct from 5 points and so on. be worried about 4-point functions at most. Okay? And an important fact that came from the radio quantization was percent correspondence, and it is important because it makes the operator product expansion exact. Okay? If you do not have conformal symmetry, the operator product expansion is just a static expansion. Okay? It's a good approximation in the ultraviolet regime of even quantum field theory. Okay? But in a conformal field theory, it is an exact expansion. Inside, it's a rate of convergence. Okay? Because recall that I have one operator here, another operator here. I can do DOPE, third operator over here, for example. I can do DOPE between these two operators inside this sphere here. Okay? And the result again was any here. Okay? So we have this radius of convergence, but inside this radius of convergence, the OPE is exact because of the operator set response. And it was the one OPE that we computed in the previous lecture. This was a confusion. The way we computed, we put another operator here and did the operator between these two, and it showed that we had here first, let's call it C prime. We had these OPE coefficients. Recall that the derivative here guarantees that we take into account the descendant fields, the descendant operators, okay, that will be responsible through the operator state correspondence to take into account the descendant states, okay. And by doing that again, by looking at the 3-point correlator, which we know to be given by this function of the structure constant, and by doing the OPE in these two fields and comparing the expressions, remember we made a Taylor expansion, we took these 2 points to be close together. And again, in CFT you can just do if these 2 points are really far apart, you can just do a scaling transformation. The theory is invariant under it, then I can do a Taylor expansion, and there's no problem with it. Again, as long as we inside the radius of convergence, okay? And by doing that again, we managed to we've learned that inside this OPE coefficient C prime, we managed to we learned that the structure constant appear inside that. Okay, the same structure constant of this 3-point function. Okay, so the OPE, what the OPE does, it takes two fields. We say we fuse these two fields in expansion of only one field. Okay, and this structure constant that appears here is the same structure constant that would appear in this correlator between these two fields that we fused and the field that appears in the expansion. Okay, and we see here again the derivative, like I said, is responsible for creating producing the descendant fields, and we see that for each term, for each k here is a primary operator that contributes to the expansion. And so what the OPE is doing basically is saying that the result of fusing these two operators is an expansion in the conformal families. Okay, primaries, a primary operator together with all its descendants. And we have one structure constant for each conformal primary. Okay, so this is the basic structure of the OPE coefficients. Okay. But then again, we are that this is not in any way determine the value of the structure constant itself. Okay, we just managed to relate the OPE coefficients, which is one concept, to the structure constant that appears in the 3-point function, which is another independent concept. Okay, we just managed to relate them, and this relation will be useful for actually computing by some techniques that we're going to discuss later today. Okay. But all this discussion leads to this notion that this set of scaling dimensions is distinct if we're dealing with more complex theories, and these structure constants. This set is what we call the CFT data, and the point is, if we know the CFT data, the value of all the scaling dimensions of the primary fields, okay, this for course, just emphasizing primaries, of course, because the descent can just get by the formal algebra by applying momentum operators. If we have the knowledge of the CFT data, we can, in principle, compute any correlation function by using the OPE, okay, recursively, because the OPE, this is inside the correlation function too. Okay. It is common practice to drop the brackets denoting correlation function, but you must keep in mind that when you're doing the OPE is always done inside correlation functions. It's an operator state. Okay, it only makes sense inside correlators. And then the question is, okay, this is the question. And the answer is kind of the answer is that there are kind of some of consistency conditions that we can impose on this FT data. And these consistency conditions will be responsible for constraining the CFT data. And if you're lucky enough to have enough really good precision in these constraints, we can determine the scale dimensions and the structure constants with really good precision, like numerically and so on. We have a specific value. Okay, the CFT has these primary operators with this scale dimension and so on. Okay, and with this knowledge, we can compute any correlator and obtain a number. I said I can in fact compute any correlator in the theory. So in the sense I solve the theory. Okay, just can compute anything that is. I can compute everything that can that corresponds to some physical quantity that can measure. Okay. So there are some consistency conditions. That constrain the CFT data. Okay, and the number of these consistency conditions depends on the specific theory you're dealing with, and all other structures that your theory can have besides conformal symmetry, like gauge symmetry, some other symmetries in general. One immediate consistency condition, if you want a unitary theory, okay, kind of an example. If you're interested in unitary theory, unitary CFT, then we have the unitarity bounds that we discussed in the previous lecture. Okay, it's a constraint for the spectrum of scale dimensions of primaries. Okay, it's just an example, but the topic of this class is the operator product expansion associativity, that is a constraint that will be present in any CFT. Okay, and it is kind of the main constraint that you can impose. Okay, and that's what we're going to discuss. Okay. So are there any questions about this? Okay, these are just the most important points that we learned so far about CFTs regarding what we're going to do today. Is it clear? I did this up for now. This review was highly based on the reference by Richcock that I gave to you. It has at the beginning of its last section that is about conformal bootstrap. He makes a review that's kind of like this. I put some more things and I took some other out, but it's a good review if you want to read about it too. Okay, so I'm expert. Okay, so OPE Associativity. First thing, it has other names. It's also called bootstrap. Or even crossing symmetry. You can have all those three names. I would tend to avoid crossing symmetry because there is another thing in quantum field theory that is known as crossing symmetry. They are, of course, not this one, so you could cause some kind of confusion. So I'm just gonna avoid the crossing symmetry name. But if you come across it in a CFT paper, then it's just OPE Associativity from a bootstrap condition. Okay, so I already give you a hint in the previous lecture about this OPE Associativity. The point is we're going to consider the OPE for scalars. Okay. Maybe so I consider the correlator of 4 scalars. And we will do the OPE. Okay. Just a continuation, direct continuation of the previous lecture where we just played this game for 3-point functions. Now we're going to play for the 4-point function. Okay? So so there are a number of ways I can do OPE here. Just choose this one for starters. Okay, I'm gonna fuse phi 1, phi 2, and I'm gonna fuse phi 3, phi 4. Okay. I should obtain something like this. Actually, a double sum A prime because I'm doing fusing 2 operators. Then I'm gonna have the structure constants. 4 prime. Okay. It's just 2 times this structure here, basically. Here just times. It's not just a times. Okay. Everyone can see that this is what you're gonna you obtain by doing these 2 OPE together. It's just twice this that structure over there. I have I have the structure. I'm using operator 1 and 2, and I'm trading them by this operator OK, and I'm summing over it, and the structure constant, the OPE expansion constant is just the function, some function ck corresponds to this operator, and this structure constant that would appear in the 3-point function of phi 1, phi 2, and this given OK. Right? And similarly for the OPE between phi 3 and phi 4, I'll obtain another primary, OK prime, that is summed here also, and the structure constant that will appear in the 3-point function of phi 3, phi 4, and this OK prime. Okay? is now some nomenclature. This function here between inside the square brackets is what we call the conformal. Partial rate. Okay, and we're gonna do separate to CPW. Okay. The reason behind this nomenclature is because all the functional structure of the coordinator is inside this conformal partial rate. Okay. This here are just constants. Okay. And I believe I'm anticipating a little bit what I'm gonna talk about. I believe when we originally discussed these 4-point functions, I don't remember if I gave you the reference, but there is a paper by Dolan and Osborne that they show that for even dimension, even space-time dimensions, the conformal partial rates are hypergeometric functions. And if you're on not space-time dimensions, then it's given, if I recall correctly, it's given by a recursion relation in terms of hypergeometric functions, or something like that. Okay? By the end of this lecture, I can give you, noted here again, I can give you the reference. Okay? So we have some kind of knowledge and analytical knowledge, at least at best, at worst. We know it's a recursion relation for it.
Can you just make one more, because I forgot it, then in the end you have to set y and z to some point in between x1 and x2? Or
oh yeah, that would be... Okay, I can put these operators
in any point between the ones, no? Or,
okay, so the picture is, for example, I have 1 here, phi 1 here, phi 2 here, and phi 3 here, and phi 4 here. Okay, so I'm basically doing the OPE here, and this is a correlation function. Okay. I'm doing the OPE here and another OPE here, so I can put the result of the OPE, say, anywhere inside the rate of the convergence, any point. I'm just using the difference, okay? So we have, I'm putting it anywhere around here. But it will just be two, but it's implied, okay? Any more questions? So, okay, so, but this choice of OPE, it's what we call some more metric, okay? We say we've done the OPE. In the 1, 2, 3, 4 channel. Okay, just nomenclature 2. That means that I fuse operators at. Okay. This can be kind of confusing, but now this 1, 2, 3, 4 in here do not mean necessarily the 1, 2, 3, 4 on the field, but the position. Okay, because if I had a more complex theory, I could have another operator here, spin operator. And what I'll be counting there in the channel is not these numbers, but the position they sit space. Okay. But we say that the OPE has been done in the 1, 2, 3, 4 channel. Okay. And the point is just an arbitrary choice. Okay. We could have done something like this.
now confusing for me, but maybe because you said, well, you have to have a certain ordering. They, like 2 shouldn't be in between 1 and 3 in this case. So doesn't
rigorously speaking, you have to be sure that you can find some sphere between these 2 between 1 and 3.
So can both?
Okay, for this coming in. By this configuration, then I'll be doing something like this. Okay?
But is it possible?
Yes, it could be possible for that wouldn't be allowed by the OPE convergence.
Yes, but
Here, I suppose that.
But so my doubt, just like maybe just a question, but isn't it like if I have fixed x1, x2, x3, x4, there's probably only one way I could do it, no? Because there can't be two ways, no? Or is it wrong?
I'm really bad at drawing. I'm gonna take one like the origin.
Yeah. So now either 3 is in between 1 and 2, and then I should take 1 and 3, or 3 is outside, and then I should do 1 and 2.
Maybe the point is because.
Or?
No, I understand your point. And okay, the answer is you have to be careful to ensure that this is inside the range of convergence for both fusings. If it's not, then maybe you could try instead of this one, maybe you could try this one, for example, and so on. But the point is, typically you can. This one, right? Yeah. Typically you can do another channel.
Yeah.
Okay, you're supposing that you can find.
Somehow hard to imagine, no? Because either 3 lies in between 1 or 2 or not. So
Yeah, it's hard to imagine. At least for me, I'm really bad with these things, and it's maybe even worse to try and drawing on the blackboard, the 2D surface. But good thing. The point is, okay. Let's take 3 for it. There are 3 points, for example. Okay.
no, but 3 I can see. I mean, yeah. But if I take 4, I do not know how to declare.
The point is, the key point is that the sphere does not have to be centered at any one of these points. Okay, so for the 1, 2, 3, 4 OPE, I could have chosen some sphere like this. And they're just almost at the surface.
Okay.
Same here. Then if this would be the 1, 2, 3, 4 channel.
Okay.
And if I want the one.
Okay. Okay, no, I see what you mean.
Okay.
Yeah.
Then I can take a sphere like this and another one like this.
I was always thinking that one point
Yeah.
has to be the center of the sphere, but then okay, then it's fine. Yeah.
Okay, it wasn't so bad to draw it.
Yeah.
Okay, the other point is you need to find this one sphere that encompasses these 2 points and no others. Okay, but this sphere doesn't have to be centered at any one of these points.
There can be different spheres, like it's okay. Yeah.
Yeah. And then you can ensure that the result of the expansion is operator is okay and okay prime if it puts anywhere inside these spheres. Okay. Is it clear for everybody? So then there's this supposition here that I can find these spheres. Okay. And suppose that I can, then if I do this OPE, okay, just it'll be pretty similar to that one. I'll obtain something like that. I'll obtain a double sum again, k prime. But now the structure constants won't be 1, 2k and 3, 4k prime. It will be 1, 3, k and 2, 4, k prime. Okay. And now here will be the. Say I put this operator somewhere in between x1 and x3. I just want to put somewhere in between x2 and x4. Okay. Or again, after making the expansion and applying all the derivatives that may appear inside here, I'm taking y and z to lie on this points. Okay. So this is a different expansion than this one, okay? But the key point here is because notice that these scalar fields are not necessarily the same. That's why I'm labeling them phi 1, phi 2, phi 3, phi 4. They can be different scalar fields, okay? So that means that the 3-point function, even if I take the same primary here, take primary O, the 3-point function between phi 1, phi 2, and O will be different than the 3-point function between phi 1, phi 3, and that same O. So the structure constants here will be different in principle. Okay? So what we can be sure of is that since the left-hand side is the same, okay, it's just a 4-point correlator. Okay? What must be the same is this whole sum. Okay? This whole series must be equal to this whole series, but I cannot compare the series term by term. I cannot pick individual terms in this series and compare them. Okay? Only the whole sum itself is the same. Okay? And this again, obvious because this is just a 4-point function. Okay? It's the same 4-point function here and there. I'm just representing in different ways. Okay? And this is what leads to this OPE associativity condition or bootstrap condition. Okay? One way people usually represent this condition is to say that they usually write it like this. This is just a sum. Here we have the structure constants. The first thing, this is not a final diagram, okay? We're not doing any perturbation theory here, and not anything like that, okay? It's just it's a different concept, it just looks the same, okay? And this just means that, again, similar to those drawings I was doing here just a minute ago. I have the fields at point 1, 2, 3, and 4. This is just a shortcut to saying that if I do the OP between these 2 points, 1 and 2, and 3 and 4, and I'm fusing this, okay, this vertex just means that I fuse 1 and 2, and this vertex means I fuse 3 and 4, and this will be just the correlation function between this 2-point function here. And then I'll be summing on all possibilities. And this should be the same as fusing 1 with 3, giving some operator here, and fusing 2 and 4, giving some operator here. Okay, and then I sum of all the possibilities. I could simplify this further because we know that the 2-point functions is diagonal in square dimensions. So this K prime would just be O. For this case, some people usually put just one O here and say we're summing over the primary is O, okay? But it's just the same idea, okay? Is it clear? It's not a final diagram, okay? It's just a useful way to represent. And this, you frequently read, okay, this is the conformal bootstrap condition, and you're gonna see this equation, sometimes without the sum, for simplicity and so on, okay? And the point is, maybe kind of unexpectedly, this condition is much more powerful than it appears to be at first.
So the what?
It's much more powerful than it appears at first.
Oh,
okay. This condition will allow us to restrict, then again, by employing numerical methods. This condition will lead to non-trivial constraints for the conformal partial waves, which we just see in this next point. Is related to the conformal blocks that appear in the 4-point function, the function f uv. And
that looks strange, though, because it's one equation. If the sum over k is large, we have like many undetermined variables, and it's just one equation. Like,
yeah, of course. It's powerful when you do numerics. And you set some an arbitrary precision, and this sum is infinite, of course, but what are you doing here is summing over primary operators in your field theory. And then you expect that once you reach irrelevant operators, their contribution not matter that much. If you take them into account, maybe you can get some refinements in your precision and so on. But for example, in the case of the 3D Ising model, you know that you can reach the critical point by tuning only the temperature, for example. Okay, so you have in this model you have one spin operator that will be just a 5 field, and you must. This is your spin field in your basic degree of freedom, and you should have only one more relevant primary operator that will turn out to be phi squared. That is related to the temperature, and say pi to the 4 is already relevant, and you can check numerically that its contribution doesn't matter much. You can add it, you get some refinements, and so on. And then you have to look to higher spin operators like every CFT, I guess I've said that already, every CFT has at least one spin 2 primary operator, which is the energy momentum tensor. And ideally you have to take into account, they will also appear inside here because we have derivatives, so we can have the index structure, we can have spinning operators contributing to this OPE. And if you take everything into account properly, what do you do? I think this is steps ahead, but the way I understand what they do is they take this OPE associativity condition for a specific theory, so you can simplify it a little bit. We're going to see one example of this. And the most useful form of this OPE associativity condition, you just you get some values for the scaling dimensions. Yeah, I guess you just get some values for the scaling dimensions, maybe guided by some unitary bounds for the lower range of the interval. And then you plug this into the numerics, and what you obtain is, okay, this set of scaling dimensions, this interval of scaling dimensions gives a consistent CFT or not. Okay, so the CFT either exists or does not exist for this given value or this given range. And then if you increase, and you do this for a finite number of operators in this expansion, of course, but if you increase these primary operators, increase your precision, do numerical refinements, I don't understand that much. What actually happens is that you can get really good precisions and determine with really impressive accuracy the scaling dimensions of this method. Basically, you just usually plot some graphs. Okay, so I have the scaling dimension of some operator here. Here I have the scaling dimension of another operator. And then I do this to some precision, including some operators, and then I say, okay, the CFT must lie somewhere around here for this value of the scaling dimensions. Then you make some better, you do this better, okay? You increase the number of operators and so on, and then you see that you start cutting this region and so on, okay? And this is really impressive because it works really well, just for this simple condition. I don't know the details of the numerics because I don't know numerics that much, but what they do is just they write the OPE associativity condition for a specific theory with some more specific simplification that might arise, and then they guess some scaling dimension values with some ansatz, some physical intuition, unitary bounds, or any other consistency condition they might have for the theory, and then they plug it to the computer. It's just about linear algebra, and then just starts running out.
Você já mostrou essas equações para o Felipe, da Bootstrap para o Ising modelo? Pode ser que, pode, estou agora aqui, mas me parece que pode ser uma coisa que você pode fazer com machine learning, beneficiente.
Sim, eu estava pensando nisso.
Talvez seria uma coisa
eu estava falando com ele,
para fazer. Assim, realmente resolver essa equação usando machine learning.
Eu sei que what they do is what they do here, they call the algorithm, I guess it's called linear programming. It's just a problem of linear algorithm. Let me work out some example. The example I actually have here is with respect to the 3D Ising model. Okay?
Yeah, perfect.
But I know they do this thing called linear programming, and I don't know if it has something to do with machine learning. I don't know much about this. Okay? But it doesn't seem to be that difficult in the algorithm. The algorithms are ready, you can just, in principle. Are there any more questions? Okay, so what are we going to do? We just showed this OPE Associativity condition for the 4-point functions. And I'm going to take, I guess, let's see this now. Okay, I'm just going to take one more formal step, then I'm going to look at the example. Okay, we're going to work out this condition for identical scalars. Okay, so we'll just erase all these phi 1, phi 2, phi 3, phi 4 tables to get some more simplification, gain some more intuition about the structure of this OPE associativity. The one more formal step I'm going to take is just going to relate these conformal partial waves to the conformal blocks that appear in the 4-point function. Okay. In some parts of the literature, people they don't make any difference between conformal partial waves and conformal blocks. They call them, use both names interchangeably, and some other parts of the literature they distinguish them. Okay, so just so you don't get confused when you try to read different words. So you have to take the relation is, if you actually make distinguishing, the relation is the following. Here we complete these 4-point functions by doing the OPE in 2 different channels, but we also know to some extent the structure of the 4-point function. That was written here in the review and just erased. It is simply the way I've written it. There is the conformal block, F, U, V, and given. Just to remind you the I don't have the definition of the UV that I took with. It's just the conformal invariance, okay? And what we do then just compare this form with the that will be over there. And the nomenclature usually goes like this. Okay? Take any one of these OPs, doesn't matter what, which one. We have something like this. Take the 1, 2, 3, 4 channel. Just for completeness, this is the 1, 3, 2, 4 channel. Okay. Here already simplifying the 2-point function because diagonals are just summing. I only have one sum here. Instead of 2. And the key thing to realize here is that this conformal partial wave itself must transform the same way as the 4-point function transforms on the conformal transformation, because again these are just actually constants. So I can write this in a really convenient form, like some function g, which is a function of this conformal invariance U in V again, with this same power law behavior factored out. Okay. This would be now this function g, which is also depends on the specific operator in the sum. Okay. More precisely, this is what we're going to call the conformal partial wave. Okay. And on the other hand, we know the 4-point function. Equal to that. Okay. So by just comparing, we learned that this g, the okay, so this is a relation between what we called the conformal block and the conformal partial wave. Okay? Just like written this point, it is evident that this conformal block, we can say it is expanded in these waves, okay? These conformal partial waves with these coefficients. Okay? And again, like I told you, these conformal partial waves are usually either hypergeometric functions or some recursion relations concerning hypergeometric functions. And so what this means is 4-point functions in a conformal field theory is ultimately given by hypergeometric functions. Okay? So like they're eigenfunctions, just like the spherical harmonicas is the eigenfunctions of symmetric potential, like in the other atom. So, okay?
Can you just, you have probably said it, but just again, the double sum k over k prime went to one sum over all because they have to be the same.
It's k dimension, yeah. It's diagonal.
Okay.
I could have done that too, but
Okay.
I had didn't know so. Yes. Which is the same reason why this is just a single sum here. Any more questions? Okay. So, like I said, in some part of the literature, because of this relation, some part of the literature people call both of them conformal partial waves or both of them conformal block. Some people distinguish between them, some people do not. Okay. If you distinguish this the relation between them, and if you look at the work that proves that this is a hypergeometric function of those recursion relations, they do for this site. Okay. Which then the conformal block is then just hypergeometric function again, but just like an expansion of your hypergeometric functions. Okay. Any questions? No. So now we're gonna take a look at one example. Like I said, it would be I'll take 4 identical scalar fields. This would correspond in the 3D island model. This would correspond to the spin fields. Okay.
What? To the spin?
To the spin degrees of field.
Because there's spin flip side somehow that's to the spin.
Yeah.
Okay.
I don't know if we're probably gonna need some of that. Continue with this. 4 identical scalars. Okay, so there are a number of simplifications that arise when you consider 4 identical scalars, namely that all the structure constants will be the same. Okay, because now they're the same field. Okay, so I'll just write lambda. Okay, lambda. Okay, so all of these that I was previously calling k, 3, 4, or 1, 3, or 2, 4. I'm gonna call all of them we're gonna call them lambda. I just call them lambda. Just one. Which depends again. I'm gonna put a note here because it depends on the specific primary. It's a different construction for each primary to the expansion. So just ordinance lambda. Okay, so now we must analyze what happens to the 4-point function as a consequence of the OPE associativity condition. And this is why I was trying to remember what the definition of the UEB was, but I guess I'll have to do another paper in my room. But the point is, we can understand this choice of channel in the following way. if I'm dealing with 4 identical scalars, okay, just the same final, then this function must be symmetric. In all x, okay? It's just the same field. Okay, doesn't matter. If you can just compute them if you want, or just straightforwardly just exchange the x's. Doesn't matter. And I don't remember the actually definition of UAV that I gave you, but I just remind you that it was given by some differences like this. Okay. K and L, and then here was something like IL and JK, and V was something other like this that was independent of operation. Okay. What I don't remember if it was like, I guess the denominator was the same, and the numerator was different for each of them, something like that. But the point is, so something like this. And the point is, if I exploit this symmetry of this 4-point function, say if I exchange, I believe, x1 with x3, this could be understood as in the OPE by just doing the other channel. Okay. Is this being clear or not? I could just take this 4-point function that we computed by the logical formalism and trade 1 with 3. Okay, and do the same. The denominator would change, and this U and V would change also because change some indices there. And another way to do this, I could just take this OPE, and I'll be, instead of doing this 1, 2, 3, 4 channel, I'll be doing the 1, 3, 2, 4 channel. Okay. And no matter what the side of the story you want to compute the consequence by, often changing these 2 points, the answer would be that the conformal block FUV would be, we would obtain this, you would obtain this consistency condition for the conformal block. And again, since they now are the same scalar, I'm calling delta, no indices, the scaling dimension. Okay? Delta is the scaling dimension of the phi field. So if you exchange x1 with x3, since the exponential function is unchanged because it's symmetric, it's the same fields, then you would obtain this consistency condition for the conformal block. Okay, here we have f u v times u over v to the power of delta times f vu. Okay, we exchange the arguments, the order of the arguments of delta. Okay, this is a consistency condition. Okay? This is one of the consistency conditions. Or one of the bootstrap equations for this model. No, not bootstrap equation is that one. Just like a bootstrap constraint or consistency condition too. So, okay. And the point is, we're gonna now take this consistency condition and express it in terms of this conformal partial waves. So if I just plug this expression there for the conformal block and the conformal partial waves, I should obtain something like this. After some massaging of the equation, get something like this. Again, lambda squared, all because we only have one structure constant now. G. Okay. So
Is it the same lambda or not?
this one
Yeah.
should be. And there are a number of ways to write this. So some people you write this as a sum rule, meaning you just take this both sides together and write it like this. You don't need to copy all of these expressions if you want. Just some forms people use to write these consistency conditions and refer to them as such. And this one here just means that somewhere inside this expansion we have the identity operator. So some people usually factor the identity out. The identity operator is an operator.
Okay, so I don't see how you get from the first to the second line. Like I would have thought that it's just
Okay,
zero
yeah.
results in the denominator, but it's somehow the
So
same.
okay, now let me
Where does
take
it come from?
It's because in these sums we have one possible operator which is maybe I should write this. The sum over all random operators except the identity.
Resulting. Okay.
And the identity is going to be to this guy and that just. Okay,
Yes.
okay. Some people refer to this as sum rule. People, I guess, in QCD, they work with the OPE, but QCD is not a conformal field theory. It has some approximate scaling symmetry in the UV, which you'll observe in the 60s and 70s, early 70s. They use OPE in the studies, and they usually express things like this as a sum rule. Okay, and has it's more or less like this. Okay? Before QCD and so on. Okay, the most useful form for us in this problem, which is the way they use to attack the problem of the 3D Ising model. This is just if you want just OBS, okay? But the way they use it, they took all operators into the sum, and they wrote it like this. Now, again, all operators, including the identity operator, lambda squared, squared, and this entire function here, whatever it is, they call it f. Okay. And it would depend on the scale dimensions. They put an L if you have spinning operators. Okay. And it would be a function of this u and p. Okay. And this whole sum must be 0. Okay. This is the form they use to, or on the form they use to solve the 3D Ising model. Because the idea to tackle this problem is, again, in the end, you'll just be guessing some you'll be guessing some scaling dimensions based on, okay, the scaling dimension of this field here. Okay, we're doing we're doing 4 identical scalars. Okay, if you're doing in 3D and 3 dimensions, the unitarity bound for a scalar in 3 dimensions would give delta should be bigger or equal to d over 2 minus 1. Alright, so for 3 dimensions, delta must be half, greater or equal to half. Okay, so they said, okay, let's guess some value for this this dimension of phi, and let's guess this interval, say half to all the way to 1 point something, and so on. And they put this interval.
Can you say again what? I didn't. No,
this would be for the delta.
This was the delta.
Okay.
Okay.
This lower bound is fixed by unitarity,
Yeah.
and they give some range here. And can, I guess if they allow up to something like 1.5 or something, I don't remember. And they just plug this here, and you can consider, okay, first I want to look only for scalar operators here, scalar parameters. I'm only interested in the contribution of scalar parameters. So the only other scalar primary, relevant scalar primary, is the phi square field. I will have to do something with the temperature physically. And you ask, I guess you also would have to guess some value for it. But the point is, you guess the scaling dimensions, sometimes based on some unitarity bounds, and plug them here and say, okay, I want to look, say, only for a scalar for now, so this doesn't matter. And this problem has a simple geometric interpretation, which is the following. Okay, this you can interpret this sum here like a bunch of vectors summing up to 0. Okay, the vectors will be in an infinite dimensional space. Okay? This would be vectors in an infinite dimensional space, and you're summing them with these coefficients and obtain 0. So you can interpret this geometrically as a bunch of vectors here. Okay. And for this sum to be possible, to be 0, you should have at least like one vector like this. And then you guess some scaling dimensions, plug them here, and look if for lambdas such that this sum is possible. Okay. If it weren't possible, I wouldn't have any vector like this, for example. So you have a kind of an algorithm is you take these vectors here.
So why are they vectors? So f is a function, no?
The function you can understand this like some vector in an infinite dimensional space.
The function is a vector in the infinite space. Okay.
That's the case. An infinite dimensional space. So you have to be careful about some things there, but
okay.
But the point is, you have two parameters here. Okay, you would have two unknowns. Okay, if you're only interested in scalar operators in this expansion.
Yes.
So you don't know neither the scaling dimension, neither the structure constant.
Yes.
So you say, okay, I'm gonna guess some scaling dimension because I know just a bit more about scaling dimension and structure constant because I have an entirety bound and so on to satisfy. And so you make some guess. You make some intervals here. And substitute them here. Now your only unknown is this one guy. This guy, again, remember, this is hypergeometric functions. You have exact expressions about them.
Okay.
Or in other dimensions, it's some recursion relation. But you know analytically if you want the form of these guys. Now that you fixed at least one range for the scaling dimensions. Okay? And then you just ask your computer to look for if there is any solution to this equation, meaning that any pair of structure constant inside some range that will make this sum equal 0. And geometrically, it's just like, I guess there is an algorithm, really simple one, just throwing out the most sophisticated one. but it's you take these vectors in this space and you try to look for a plane that separates all vectors to a single side. Okay, so if I can find some plane here, such as every vector is above this plane, then that sum cannot be satisfied. If I cannot find such a plane, then that sum can be satisfied. And
Then
so
what?
the sum can be satisfied.
Then what?
The sum can be
Sum
satisfied.
can be satisfied.
If I can find some plane like this,
But
then this sum can in principle be satisfied, and we have a range.
Just
for this.
the lambdas have to be positive or something. Ah, no,
Yeah,
this
they
one
have to
is
be positive.
yeah,
Okay,
yeah,
this
yeah,
is a specific case. And again, you're right. I should have emphasized this point. For this
Yeah.
specific case of 4 identical scalars, we know that this guy will be positive. Okay. So that's why this algorithm works for this case. But it's just like an example. Okay. Most of the case, I don't know the algorithm because again I don't know much about numerics. But the routine is like something like this. This is just the bootstrap equation that I wrote here in terms of those things that look like fun diagrams, but are not. I just simplified it a little bit because I'm dealing with scalar, identical scalars. And I simplified to this form. I know these guys, again, geometric functions. And I just get some values for the relevant scalar primary operators that will appear in this expansion. And look for the solution. I numerically look for solutions of these equations, okay, meaning a set of structure constants. Okay, values of the structure constants. Okay, that make this equality possible. I can either find a solution or not find a solution. If I do not find a solution, the CFT does not exist. The CFT with these given values that I guess do not exist. If I can find a solution, then it exists. Okay. And then later on, by including the contribution of spinning fields.
Can I just so this is like what I understood so far is if I have as an input, like I have an idea of my primaries,
I have
an idea of my primaries.
this can be there, this can be there.
Yeah, and it's okay. But now why did I need delta phi squared? This I didn't understand. Like so where did delta phi squared enter? Like I have one scaling dimension for delta phi. So I say it's I have a lower bound. I take the range.
It could appear inside this, like a previous video. This is an expansion of primaries. Previously, this is an expansion of primaries, relevant primaries or irrelevant primaries and so on. Okay. Then usually you just look for relevant primaries if you want.
Yeah.
I guess they usually include the first irrelevant primaries too. For the case of the Ising model, it is phi and phi squared. Phi to the fourth is an irrelevant operator in 3 dimensions. For scalar field in 3 dimensions. And the first spinning primary operator to enter this contribution, this expansion is the energy momentum tensor, which has the energy momentum tensor is kind of special because it has no anomalous dimension. Okay? The energy momentum tensor we have for the Ising model in 3D. For 3D theory, we have a scale dimension 3. Again, because it has to do because the integrals of the energy. We're going to discuss this maybe in the next lecture. Okay, but if you want to take into account the energy momentum tensor, you can just take delta to nu equal 3. Basically. Has no correlations. But we'll come to this. Don't have to be much sure about that at that point right now.
Just sorry. Now, in case of the Ising model, so can you say that like this has been done for the Ising model, and how many primaries did they, or like what were the fields? Okay,
so I'm going to give you a reference, and I'm going to tell you what I remember from the top of my head.
Okay.
This will not be everything. Okay, this is basically what I had kind of prepared for this class. Because if I want to do to look at this example further in more detail, then we must resort either to, if we do not resort to numerics, I have to open this function in the geometrics and the recursion relations, and this just be a computational hell that doesn't have much point. You can just look at the papers.
But just to have an idea, like, is there now how many terms do I sum there? Do you know? I mean, in the end, how many?
In principle, you should have some infinite sum.
No, but I mean in this example of the Ising model.
In the Ising model,
how many? Do you know that?
I guess they wrote like a table. They had the phi field they called sigma for the spin. They had the phi square, which I believe they called epsilon prime. Epsilon. The reason that when you usually dealing with strongly correlated systems, it is nice to give other names. Because you know the fundamental field, if you have a Lagrangian description of the fundamental field is phi, you can have phi square, phi the third power. But as we discussed, I already gave you the numbers. The scaling dimension of phi in this case is actually pretty close to an exact count. I guess it's 1.51, something like that. But if you apply your intuition of standard quantum field theory for weakly coupled systems, then the dimension of this guy should just be twice this, which is something like 1. But in this 3D Ising model, which is a strongly correlated system, this scaling dimension is actually 1.5 something. So it's really far away. Okay, so to free ourselves from this notion, they usually just give different names. Okay, but if you could map then the sigma, if you read the paper, they're just gonna say sigma, epsilon primary, and epsilon prime primary, and so on. But then have something like this. The phi 4, I guess they call epsilon prime, but it's already these are relevant. In the renormalization group sense, this is already relevant. They also consider the energy momentum tensor. I don't remember if they called it new or gave another name for it, which is what's kind of marginal. It has delta equals 3. They classify the primaries as by spin, scalar primaries, spinning primaries, and further separate them in Z2 even and Z2 odd, meaning if I take the operator, if I take 5 minus 5, so this one is Z2 odd, and this one is Z2 even, so on. So they classified them operators, I forgot something. They had some spin 4 operator here too. I don't remember. And there were some other operators here.
But let's say
I guess
less than 10 or
less than 10. Yeah, less than 10. There was some operator I guess they considered was this operator here, the energy momentum tensor times phi squared. It is a primary. Again, why is it a primary? Because you cannot write this as a total derivative of something else. Okay, so this operator will show in this expansion somewhere, but it will be irrelevant. They include the first few irrelevant operators. Okay? Yeah, there are a bunch more. Not a bunch more. Less than 10. I guess around maybe 6, 7. Probably there was some sigma prime, but
and to, if you would like to try to improve their result, it's not about solving the equations, but you would have to find more operators. Or
yeah, that is a way. You asking about this specific example of the 3D Ising model.
Yes.
Yeah, one way would be to. I'm supposing they used eventually. I'm supposing they use the explicit form of these guys.
Yes.
So I guess in the first estimates you can make some expansions here to simplify a bit. I don't know if they did this for every estimate they did on the paper, I don't recall, but suppose they did not, one way to improve too would be to use the exact expressions. That, you know, it is some arithmetic function or recursion relations. Another way would be, of course, to include more primary operators. Relevant. They took into account all relevant primaries. Right? All relevant. That's for sure. If you take into account more irrelevant primaries, then yeah, they could improve a bit. And for this case,
So, because I just don't have any understanding of, did they take into account all the primaries that were known, or did they say, are there more known and they just didn't take it into account? Do you know? Okay.
no, because in terms of this, at least in terms of this, no, sorry, you're talking. I was thinking something else. You're talking about primaries, right?
Primaries, yeah. Or is it just
Relevant or?
so what
They did-
relevant they took into account?
Yeah, they did not. Okay, they certainly did not take into account every primary. Because, okay, this is a primary, okay, then probably this here is a primary also. So it's like,
Okay.
so, but of course this will be too irrelevant, so you usually classify between all the symmetries you can have, continuous and discrete symmetries. This is one discrete example, the two orders, the two even operators. And the reason is because if you, this was the, in this language, this was